But I am pleased to be asked to speak here. There we go. Should be full screen now. All right. And I need to shrink this down for me so that I can, there we go. So I can actually see the screen myself. First, I wanted to make sure that folks online can actually hear me.
Yes, everything is perfect.
Okay, excellent. So we've already heard the title. I'll give just a quick, since we're starting a little bit early, I'll spend a slide just talking a little bit about my background. As Bronis mentioned, sort of in the late 1980s, both myself and Vaidi Sundaram, he was a visiting faculty from Georgia Tech that came up to Oak Ridge, actually from Emory at that time, came up to visit for a summer at Oak Ridge National Lab, and he and I came up with this thing called PVM, which then went on to become very popular around the world for distributed computing. But then when it comes to MPI, when we first started the whole MPI adventure, I was picked as one of the leads in that MPI 1 forum. And what I call up here, it's the fun and games at Dallas-Fort Worth Airport. I'm not sure anyone here is old like me that actually remembers going there every 2 weeks for a year to come up with MPI 1. It was Tony Skellum actually would remember. I was checking to see if he was going to be here in the audience, but he wasn't. So he was also one of those that was at the Dallas-Fort Worth Airport every 2 weeks for a long time there. And then, that settled down for just a short period of time before they already started to say, yeah, but we want all those features that MPI has, or that PVM has in it. So can you put those into MPI? And it sort of kicked off the MPI 2 forum. Can't say that we put all those features in there. But again, I was picked to lead up one of those areas. And so they changed locations, and was done at the Chicago O'Hare Airport every about 3 weeks for even a longer period of time before we actually got that done. So that's back when I was young. Today, I'm one of the leads on the Exascale computing project, and I was deeply involved, as Bronis mentioned, in the procurement, delivery, and installation of this first Exascale computer called Frontier, which is at Oak Ridge National Laboratory. So in this talk, we're just going to learn a little. I suspect you guys are way smarter than me and probably know more about OpenMP and MPI at Exascale, but there'll be a few things that you'll learn about today that it's not public knowledge. Will be after this talk, though. So this is the US roadmap to Exascale systems. It's just the roadmap since 2012. And I wanted to make 2 points. One is that Europe and Japan and China also have roadmaps. They're not displayed here. In this particular one, you can see we've got highlighted Frontier, Aurora, and El Capitan. Right now we're in 2022, so the only one that exists is Frontier, and that's what we'll be talking a little bit about today. But I wanted to make sure that that the others were highlighted in the sense that over the next few years, we're going to be trying to put in a series of at least 3 Exascale computers. And that second point was about, this is why is it 2012? It turns out that there was also a plan to be able to use these Exascale computers that were highlighted. And indeed, it's this Exascale computing project that's run from 2016 to 2024. And you might say, well, but wait, Al, you just told us that the roadmap started in 2012. How come this starts in 2016? Turns out that I was tagged by the Department of Energy to write the mission need statement for the Exascale computing project in 2012. And it was rejected. So I did a really good job, evidently. In 2014, they came back to me and had me work with Bill Harrod to try again. And some people here will actually remember the era where we were working with Bill Harrod to try to come up with an Exascale project. And it failed again to gain traction in the US government. They just said, no, not what we want. Doesn't look like it's what we really need. And it wasn't. So a couple of years later, I was tagged once again to try to write a different mission needs statement. And either because the landscape had changed or the political climate had changed a little bit, it got traction, it got funding, and it finally took off in 2016, even though our roadmap had sort of been running from 2012. We actually did begin what is sort of the very first part of the Exascale computing project, which is way over here in the side corner, this hardware technology advances. We started something called Fast Forward and Design Forward in the 2012 timeframe, and it was funding vendors to get the technology ready for Exascale. So we were starting that roadmap up even before the Exascale computing project really kicked off. Once it got kicked off and had its funding, the design forward efforts, the vendor efforts were rolled into the Exascale computing project. And that's why I say here that the Exascale computing project is huge, still going on. It goes on until 2024. It involves 15 national labs, 32 different vendors, 70 universities, and over 1,000 researchers. In many senses all around the world, because there's some funded outside of the US. Inside of this Exascale computing project, there are kind of 24 big application projects. But those application projects aren't just 24 codes. There's actually 78 separate codes inside those application projects. And there are, I just realized that if I don't stand in front of my computer, they actually don't see me online, which is probably better, represents over 10 million lines of code. And all of these codes, these applications that first started as MPI or MPI plus OpenMP on CPUs. So that was kind of our starting point and the segue about how ECP and OpenMP and MPI kind of got started. But another part of the ECP project was the software technologies effort. And it, again, has a lot of different products, different software products that come out of it, but it actually involved multiple MPI efforts inside of there. Those 24 applications actually were handpicked because of the broad portfolio of applications that they cover. I'm not going to go through all the details on this slide. What I'm mainly going to do is hit the top line, which is the kinds of areas that were covered, deal with clean energy, economic security, scientific discovery, basically climate change or Earth system models, healthcare, and national security. And at the end of the day, even though we went through this process both in 2012 and 2014 and 2016, this was the way that we basically sold the project, that these were all areas that were really important, not only to the US, but to the world to try to solve. And that's why we needed exascale computers, and we needed this development of the applications to be ready for these exascale computers that on the roadmap weren't going to show up until 2021 or 2022 kind of time frame. So let's look at inside those applications, and what we see, this is an interesting diagram. We'll spend just a little bit of time on this one. This is showing, first off, why MPI and OpenMP, how they dominate the ECP programming models. But what you want to look at let me first describe what the diagram is. So it's kind of the height of the bar is how important is it to applications, lots of different applications and their need for it. And it's really the height of the blue bars that are key, because the highest bar across this chart is the one way over here on the edge called SPAC. But you'll see that its blue bar is very short. It has a very tall red bar, but from a standpoint of being critical, it's not very tall. The critical ones are LLVM, and we'll hear a little bit more about that during the IWOMP tomorrow. But the other two tallest ones are OpenMP and MPI. So of the most critical applications or programming development, those are there. I wanted to go back and try to highlight what are some of the other interesting competitors to that, things like Raja or Cocos and C++ and Fortran, in terms of why aren't they even taller than MPI? They're not. And so it's sort of interesting to see all the different ways, even CUDA. It's got a large number of things that we've SYCL, for those that know what SYCL is. Just sort of, in some sense, how important each of these packages are to the success of these exascale applications. And so MPI and OpenMP certainly are way up there in terms of being kind of the most important things for us to get right if we want these exascale applications to be a success. So why is this exascale application development so hard? Should we just code it up in MPI plus OpenMP and we're done? Should be a piece of cake. But over here are a number of reasons. I got a couple of slides on all the different reasons. First off is that, remember, we started with OpenMP plus MPI on CPUs. And over the ECP's lifetime, it's been running on for about 7 years now, been really a lot of changes because the teams have looked at those codes. They've gone and in many cases changed their methodologies. They've changed their algorithms. They've even changed kind of the physical models that they use to be able to solve these problems. And every time that changes, it changes the way you have to adapt both the MPI and the OpenMP aspects of it. The other thing that we've seen both over this 7-year lifetime, but certainly in the last 2 or 3 years, particularly since COVID, is that HPC expertise has become very limited. So the number of people that actually know how to program for really big systems has become really hard to find. And we find that even worse as we have started to work on Frontier, and we find that the engineers that are inside of the vendor companies don't really have the expertise of what it means to try to work with a machine that has tens of thousands of processors in it, and the reliability and the stability kinds of issues that you see in that environment that you don't see when they're just talking about a hyperscaler data center or a cloud provider. They think of, there's this Kubernetes layer. It takes care of all the resilience that I need. If anything fails, it'll be restarted, no problem. They don't understand that on these really big systems, all of the processors are being used to solve this big problem. And if one of them goes away, it can just blow the whole rest of the application away. It just stops. And it's like, that's not the mode that they have grown up to learn about from the data centers. And so we have them developing software for these systems like Frontier and El Capitan and so forth. And we have to make sure that they've come to an understanding. And even right now, as we're putting Frontier through its paces, through acceptance, we're struggling with this idea of, that this is not good to simply assume that the network is always up or that every link always works. Because we actually had them tell us that, oh, well, we just assumed that all of the global links in your machine will always be up. So we didn't write any software to deal with it if it's one of them is down. Well, we're seeing 5 of them down right now, and it's not working. So what's another issue besides the expertise? It's that the programming models and analysis tools, so the compilers, as we know, things like LLVM have evolved and in fact seems to be kind of taking over. A lot of the other compilers are falling by the wayside or being absorbed underneath in terms of having LLVM. And so the community is having to adapt to that. But this bullet is all about how long does it take you to adapt? So it takes time for all of these things to mature. The whole idea of co-design is something that was really big in the frontier, this Exascale roadmap that we were seeing. There are several years of development of technologies that are important to try to get there, but it's all about timing. How do you get all of this done at the right time frame? And then at the very end of the day is you need broad community buy-in to the new technologies that are developed. You don't have them coming back and saying, no, we didn't really need that, or we don't like the way you've done it. Application level libraries, this is really more specific to people that are doing the application development, but they typically are developing these libraries, but they will develop them and oftentimes tune them to a particular machine like Summit or Sierra, and then a machine like Frontier or Capitan comes along and they have to adapt and evolve them to the new machines. And so again, there's a limited number of people that have developed those application level libraries that have to be done quickly. So these are some of the reasons why development is so hard. One of the hardest parts is the last bullet, which is that all of those yellow machines that I highlighted on the first slide there, all those Exascale machines use GPUs. There aren't multiple architectures now in these machines. They're pretty much a CPU, GPU kinds of machines. And even though vendors will claim that GPU hardware is general purpose, there is a preferred computational motif. And this next slide kind of tells what are some of the big problems, but also some sense programming tips. But GPUs do best for codes that expose massive parallel, fine-grained parallelism. And what do you mean by massive? Well, on Summit, when you do the math there, you can see there's 73 million way parallelism in the system. And so we had a tutorial this morning on multi-threading, and you're now trying to think about how do you write your programs that have this much parallelism in them all the time. Frontier and El Capitan are going to have even bigger numbers than this. It's best for codes that can be GPU resident. So we've seen a lot of applications, they start out on the CPU and then they do a little bit of the offload of the worst parts of the code or the most computationally intensive parts onto the GPUs. But it turns out that data movement back and forth between the GPUs and the CPUs was very much a restriction. In the earliest days with Titan, the first system on that roadmap, there was only a very small pipe between the GPU and the CPU. And therefore, anything that had to flow back and forth really slowed down your application. What we see more and more as we move forward is that application developers are trying to figure out ways to stay much more resident on the GPU and get all the work done there so that there's much less data movement. There's also another big advantage not listed on the slide is that the speed of the bandwidth of the memory on the GPU is so much faster than it is on the CPU that even though you say, well, I moved all that CPU stuff on the GPU and it's not really best suited for a GPU, a lot of times you still come out ahead, not only because you don't have the data movement, but just the bandwidth itself to that memory is so much higher by an order of magnitude. But the GPUs, in terms of actually getting work done, the reason why you have to, on all of these Exascale systems, try to make things resident on them is that all of the real horsepower, the flops, are there within the GPUs by 2 orders of magnitude. So if you look at both Summit and Frontier, both of them, when you look at how many flops are generated by the CPUs. In the case of Summit, it's like 2, and there's 200 petaflops total in it. In the case of Frontier, it's more about 20 petaflops in CPUs and 2,000 petaflops in GPUs. And so if you want to run fast, you want all your code to be there in those GPUs. This doesn't do any good to be on the CPU. It's so much slower. So the other thing in terms of how do you take advantage of these GPUs is you need a lot of arithmetic to be done relative to off-node communication. So this isn't talking about on the node between the CPU and GPU, but now taking it up one more level and saying, well, what if I have to go off the node to someplace else? And so you want fairly large nodes with a lot of memory. That's what we have discovered as we moved along our roadmap. If you give the users a lot of memory space on a particular node, they can sit on it and grind for a long time before they have to send messages off. And again, that boosts their overall efficiency in terms of being able to solve much bigger problems. There's something that happened about halfway through our roadmap when we got to Summit. And it was interesting. It was the Tensor Core instructions. In AMD, they're just called matrix instructions, but they're basically special instructions built into the GPUs to go even faster. Basically, the way I think of it is, it's like back when we developed the BLAs, and you had the first level 1 BLAs and level 2 BLAs and level 3 BLAs, and the Tensor Core is like level 3 BLAs. It's a little matrix of operations, and you can do it all in just one call. And you can take big advantage of both locality as well as data movement when the hardware knows exactly what operation you're going to do in 2D, in a 2D matrix operation. Now, NVIDIA stuck that into the Summit and Sierra machines without actually telling us. We worked with them for, 3 years on this computer, co-designing it, and they never told us that it had this in it all the time until after it was delivered, and we accepted it. And then they said, oh, by the way, there are special instructions in here that your application teams didn't even know about and have been developing codes without knowing about them. But they have now become so much faster by taking advantage of them by factors of 2 to 8 speed improvements by taking advantage of these Tensor Core instructions. Now, as we move to Frontier, you want to try to take that into consideration. You know they're there. Go ahead and try to write your codes to take advantage of them. That's true. And on Frontier now, that's also available in double precision. So you can do these matrix instructions in double precision. Let's see. Operating in a weak scaling regime, really trying to get, so this is trying to say, we've taken it each step. One is between CPU and GPU, where do you want to try to put your codes? Getting between nodes, and now between nodes and storage. Sort of the obvious thing is that you want to have a relatively high flop rate before you're trying to write things off to storage. So that said, let's talk a little bit about Frontier. So this is the first exascale system to exceed an exaflop on the top 500. That is a very accurate statement. Whether it's the first exaflop in the world, Chinese might disagree. Again, I don't know for sure, but we know that it's the first one to exceed an exaflop on the top 500, and it's also the first to exceed 20 megawatts per exaflop. And that's actually probably a more important thing to each of the other, the Europeans and the Japanese and the Chinese, in terms of, as you build these really big machines, the amount of energy that they consume is really important to not only the data center, but to the country that's trying to run them and pay for the energy that's used to run them. And so turns out that Frontier makes a really big leap forward in terms of the amount of energy efficiency we have. These numbers down here on this slide kind of point them out. I wasn't going to go over them in any particular detail. What I was going to say, though, is that let's think about those application teams. Do we actually have all the teams are very eager right now, I know, because I'm on that ECP project, and they are continually asking me, can I get on it next? Can I get on it now? Can I get on it? And we actually did let a couple of the teams get on to try it out. And we actually have a list of teams to call at a moment's notice that are a part of the ECP project, part of that big portfolio of apps. We've kind of gone through the apps and said, these are the teams that have two characteristics. One is their code is very ready to go at scale on Frontier. They've been using a test and development system. You see it kind of mentioned in the very first line there, 128 node system that they've already compiled their code. They've already scaled it to that size. They know that they're ready to go. And two, that they are what we would call hero users. If they get on and the thing blows up the first time they try, or the compiler doesn't work right, or MPI has some weird errors that it throws, they don't just go whining about it. They just try to figure it out and go on and try to solve this problem. They know that they've been given some special opportunity to get on the machine early. So we've got a list, and the first two on that list were WarpX and Exascale. So WarpX is an accelerator simulation model for building things like the Large Hadron Collider in CERN, or the linear accelerators all across the world. And Exascale is basically a model of the entire universe from the Big Bang to why do you get these filaments. So it's really not looking at why do galaxies spin the way they do, but really why is the biggest picture, this thread-like model with dark energy and such, how does it interact, gravity and everything from the Big Bang out? Can you simulate that? That's what Exascale is doing. Now, all of the ECP teams, or at least the application teams, they've been given a goal. They are supposed to be able to run at least 50 times faster than when the Exascale project started. So in 2016, they benchmarked all their codes. And when an Exascale computer shows up, they are supposed to be able to in some sense, pass their goal. They have to be able to run 50 times faster. So these two guys, they were only on for, one was on for about 3 days and one was on for about a week. And yeah, Frontier was kind of flaky and they were dealing with various issues, but WarpX was able to get 110x speed up. And Exascale was able to get a 236x speed up over what they could do before. So way exceeding what their main goal was. And it's really showing that Frontier is a beast. Not only is it very energy efficient, when you get your code running, if you can get it to go through, it just screams on that machine. So there's a lot of excitement by the rest of the teams. They're all very eager to try to get on. The only way they get a call right now is we're going through acceptance, which is a whole bunch of tests that we have to run on the system before we can turn it over to production. And if we ever run into a snag and say, oh, well, the vendor needs to go fix this MPI problem, or the vendor needs to go fix this IO problem, then we don't want the machine to sit idle while they're doing that. And we will call these people up and say, you got 6 hours, go for it. You got the whole machine for the next 12 hours or something. So there's a list and we call them up whenever. So far, only 2 have gotten the call, but each of them has been able to do very extraordinary performances in that short period of time. Let's just talk a little bit. I don't know how much people here know all the details about Frontier. Maybe I'll be boring you to death. But it's sometimes important to try to understand what the machine looks like if you're going to be writing MPI and OpenMP code for it. It's 2 exaflop peak double precision. And I say peak double precision flops. It's sort of interesting because these machines, to say what is the peak, and if you look up in the top 500 list, has a different number. It's about 1.6 is what we put in there for that. The 2 exaflops that I put on here is what I have actually measured on the machine. So it's not a peak number by saying, well, this is the number of units times the frequency times the is equal to 2. No, this is a number that I've actually measured doing dgem across the entire machine. So it actually can run at this speed. And the thing that makes it hard to understand what is the right peak rate is because these modern machines are complicated. Okay, so you have a GPU, and it turns out that the GPU is very sophisticated in that even different, it's not just that the different chips on the node can run at different speeds, different parts inside the GPU can run at different speeds all at the same time. So one part can be running at a boosted speed and another part running at a lower speed. And it's all about energy use in some sense. It's capped at a certain amount of energy can be used in this machine. It turns out that 2 exaflops is sort of at the optimal combination of how much of the chip is running at a certain frequency so that it uses the amount of energy less than the 29 megawatts. In fact, it was about 23 megawatts when it was running at 2 exaflops, but it was just doing dgem. So there was not energy being used to do a lot of IO or communication. The other thing that's sort of amazing about Frontier is how small it is. It's only 74 cabinets. So when we first thought about these exascale computers and we were trying to build the buildings for them, we thought, my gosh, it's going to be 200 cabinets is what we looked at when we were building Sierra and Summit. There are like 256 cabinets, I know, for Summit. And we were thinking these machines are going to be monstrous. It turns out that I called it extraordinary engineering, but they packed a tremendous amount of the transistors, copper, into a very small space. When I say small space, so yeah, the whole machine only takes up about 4,000 square feet in its footprint. So that's a fairly small computer room, but each one of the cabinets weighs 8,000 pounds, empty. It's water cooled. Without water in it, it still weighs 8,000 pounds. In fact, when we discovered that, and it was a little bit late in the process when we discovered that, we had to actually rip out the computer room floor that we had put in and replace it with a much stronger floor just to be able to hold the racks, because it's not just one 8,000 pound rack. It's a whole row of them. So it was an adventure. The 29 megawatts is where we got, this. If you take 2 exaflops and divide it by 29 megawatts, you can see this idea of exceeding the 20 megawatts by a fairly large amount. It's more like 14.5. So, and we'd say, yes, but can that machine actually pull, go above 29 megawatts? Maybe you're just kind of making that up as the best megawatt number. No, actually, that is the peak power that's actually possible in this machine. Each one of these cabinets can only supply 400 kilowatts, which is a lot. But if you take 400 kilowatts and multiply it times the 74 cabinets, so you max out this machine with as much electricity that you can put into it, it still only comes out to be 29. And you don't really run the machine up at that level, but that's just the maximum it could possibly do. I'm just going to say one more thing here. I'm not going to talk about the node. I've got a a whole slide on the next slide about that. It's just that the compute blade, I thought it was interesting just to show it because you can see how thin it is. But the fact that a compute blade really has two nodes on it. So each one of those that slides into the computer has each one of these nodes. There's two of them on every blade. So what are some of the interesting features about this particular node and some features that are important for MPI? First off is that everything here is fully connected. So if you can see from all the arrows, all of the CPU is connected to every one of the GPUs. Every one of the GPUs is connected to each other and back to the CPU. It's got an AMD, what we call a Trento CPU. It's a 64 core. If you're interested in trying to figure out what kind of multi-threading you would need to run MPI on it. And it is basically the Milan high-end 64 core CPU, but we actually paid AMD additional money to come up with a custom version of it that they called Trento, and the custom parts are what the bullets here are describing. So it needed to support Infinity Fabric, and the reason why Milan doesn't, and the reason why we wanted it is because we wanted this to be coherent memory across the entire node. So all the memory on the GPUs and all the memory on the CPU would all be visible to everyone on the node. And the Infinity Fabric allows us to do that. The other thing that we paid them extra money for was to put 4 terabytes of non-volatile memory on this node. So it gets back to what I was saying before, that if you give the user a lot of memory on the node, then a lot of times they can decrease the amount of information that has to flow back and forth between nodes in the system, and they can run more efficiently. And so we had to put additional PCIe links on that Milan to turn it into a Trento, just to be able to support the links going to that non-volatile memory. And so each one of these CPUs got a 0.5 terabyte on it. Then we'll talk about the GPUs. So there are 4 of those. One of the things that's important in MPI, and I'm not sure that how well it works today, it works. How well it works remains to be seen, is GPU direct sends. So think about your codes running resident on the GPU, and it's done some calculation. And in fact, you want to try to keep all that work on the node so you don't go off node. You want to send that message to this other GPU, or that's the place that it needs to go next. And so in the old days, like with Titan, that MPI message would go back to the CPU and then come back out to the GPUs. But here on Frontier, all of the messages can flow directly back and forth between the GPUs, and it has the advantage that everything here is shared memory. So if this GPU really needed memory that's up on that DDR, it could address it directly and pull it as well. Part of what I mentioned before about one of the big advantages to try to stay resident on the GPU is how fast the memory is. So on Frontier, it's 3.2 terabytes per second memory bandwidth to the memory on that GPU. So it's much higher than what we can get from the DDRs. So if you can take advantage of the bandwidth, there's a big win there. There's a drawback to using HBM memory though, and that's the latency is much higher. So what you want to do when you're programming this kind of machine is you want to take advantage of latency hiding. And it turns out that GPUs are very good at that because they like to work with vectors. So you can try to write your codes in a way to take advantage of that. Another advantage that we had here with Frontier that we didn't have with Summit or other machines is that the communication to the network comes directly from the GPUs, not from the CPUs. So back with Summit, all of the information that needed to be sent from one node to another node went back out through the CPU because the NICs were hooked onto the CPUs. Here, we're trying to make sure that people get into the mindset of running resident on the GPUs, and then when they need to send something out, there's actually a NIC hooked to every single one of the GPUs. And the first question that came to my mind was, yes, but can I take advantage of all of the NICs? Am I just limited to the speed of this link? Can I actually have information here that I want to send to another node and take advantage of in some sense, bonding all of those together? And it turns out that that actually is possible. Both the CPU as well as GPUs can take advantage of multiple NICs, and it will route through this link to get to this one, sends out that one directly, and so forth, so that you can take advantage of multiple NICs if you want to boost the speed of the network. Then the last thing I wanted to mention on this slide is that this MI250X is really not just a single GPU. It's actually two GPUs. It's actually just one GPU with two things on it that AMD calls GCDs, which is just basically GPU. But by understanding how it works under the covers, you can take advantage to improve the efficiency of your code. First off is that we have already seen early on with Frontier that MPI can run faster if the node is programmed like 8 GPUs rather than 4. Even though technically it has 4 GPUs, it really has 8 GCDs, and they are connected through these big black links such that they can be addressed and used like 8 GPUs. The other thing to think about is not to exceed the nearby memory. So even though this GPU has 120 gigabytes of HBM2, when you actually look at how it's built on the inside, each one of these blocks is connected to 2 of the HBM blocks on either side. So each has 64 gigabytes of HBM, and then between them, they have a connection that is faster than the big black lines, but is still limited compared to how fast things work just inside the GCD itself. I'm not going to spend a lot of time on the interconnect, but it's the next logical step as messages are flowing around the system. The Frontier Interconnect is a 3-hop dragonfly. When I talked to some of the other folks in Europe about a month ago, they were saying, oh, should be like a 2-hop, but it's actually 3. The way it works is it has one hop inside of a cabinet to get across cabinets, up to 2 hops to go across and get to the next cabinet and then down. So I didn't describe that correctly. It's 1 hop to get out of a cabinet, 1 hop to get to the next cabinet, and 1 hop to get down to the node in that cabinet. So it's a 3-hop dragonfly topology. The multiple hops that I described is what happens when it starts doing adaptive routing or congestion management and actually tries to take non-minimal paths through the system. Kind of the big thing I wanted to point out on the interconnect, other than the fact that it's a little bit flaky these days, is that the Cassini NICs are actually designed to do collective communication. We've been wanting hardware collectives for a long time on these big systems. There's a huge potential for running very fast in that case, and I'm happy to report that it's not implemented yet on Frontier. We're still waiting for that. So it's there under the covers, but TBD on how well it works, and we need to find that out. Just a quick thing here for folks that are interested in doing applications that are more AI or data analytic. By having this large amount of node local storage, in the case of Frontier, we've got 37 petabytes. And so the big advantage is you can look at the kind of speeds, 60 plus terabytes per second, that you can read and write into and out of that memory. Gives you a huge potential compared to having to write things out to disk or even to a performance tier. So that's a big advantage. And then the ability to do 11 billion IOPS. I saw recently where, I think it was Google, was making this big, wonderful claim about how using their big cloud center, they had been able to show that they could use all these thousands of nodes to get to 11 billion IOPS. And it was so great. And it's like, well, this machine can do this all day too. So it doesn't take a giant cloud to do that. Okay, I've just got a few more slides. I'm going to be talking about some of the problems or issues that we have seen both with OpenMP as well as with MPI. And this one, we're going to start with MPI. So this is an early, I said initial, graph. This is a graph of trying to run HPL on Frontier back in November. And it's the number of flops on the vertical versus time. And what you see is that, in fact, the profile of the top of this curve looks like exactly like what you would expect. So it winds up pretty fast on almost any machine that you run HPL on, stays pretty flat for those time that you're solving the biggest, the big part of the matrix. And then as the matrix size gets too small to really take advantage of all the hardware that's there, it slowly falls off, as you see like this. All well and good. But this is the graph that we were getting out of Frontier. And this performance nowhere near what we ended up with at the end of the day, because there's all this white space. This is not doing arithmetic. You can see that it would run almost to the peak rate and then almost in a very regular pattern, not even a compressed pattern, which really confused us, because as the rows got shorter, you'd expect these to get closer together if it was something to do with rows. It would just drop down to almost zero performance and then almost instantly jump all the way back up to peak performance in a very sharp over and over and over again. And we scratched our heads for a long, long time trying to figure out what was causing this. Now, of course, in retrospect, I can write it down in a paragraph, but at the time, it took us like 2 months to try to figure out what was causing this behavior. And we kind of guessed early on that these regular oscillations, which I told him, I said, well, what this looks like is that you're stalling the entire system. It's dropping to zero. Basically, there's nothing for it to compute. They say, oh, it's all overlapped. Everything is overlapped. There's no way. And I said, this thing's dropping down to zero. There are no nodes doing anything during that instant that it's down at the bottom. It looks like it's doing a sync or something. It is either starved for information or it's just stopped at some sort of sync point. And after a couple of months, they did find out that indeed it was in Cray's MPEG library that caused the problem. And it was a very interesting, subtle sort of thing. It wasn't obviously in the MPEG library, although creating a new version of the MPEG library made it go away. It turns out that somewhere back in the development of the fabric, and that's when we first saw this, and said it looks like it's stalling. We thought that it's probably the fabric is going bad. It's not MPI. In the end, we found out that it was MPI, so we were kind of looking in the wrong place for a long time. It turns out that in libfabrics, there is a switch called FI source. Fine. What does that have to do with anything? Well, it turns out that that's used when you're first developing your fabric and you're seeing problems and you need to try to diagnose it. So it's kind of like a debug switch. It's what it's kind of like. You flip it on so that you can find out a bunch of information about how the information is flowing. And the man page we looked at after we found this particular thing had gone wrong and fixed it. The man page very clearly said, don't turn this on because it will adversely affect performance. That's a quote out of the man page. And evidently no one had read this or paid any attention. But when we found out that in fact this switch was turned on, HPE just went out and produced a version of Cray impitch that avoided that being flipped. When we did, we started getting the curves that just looked like a line drawn over the top of this. And that's what ended up the machine looking like when we got it to exceed an exaflop. But for the longest time, for months, we were sitting there and it was all because of very subtle things that can happen on these big machines, in this particular case, inside of MPI. And then got a couple of slides on OpenMP, and I don't really have the details. I wanted to try to find them. Turns out that our IT department at Oak Ridge has brilliantly had let a license expire for our ECP database, so I couldn't actually go find the. So this particular paper is in our database, published in December of 2020. It's put out by our application. So our application teams put information into Andrew Siegel and Eric Drager run all the application development teams. They oversee them. And they gather information every year from the teams to see what are the issues that you're seeing, what are the things that you see that work good or that you've changed, what is sort of the interesting themes from over the past year. And these are the ones that are in the 2020 report. I reordered them in the interest of this group by putting the OpenMP one on the top, and that the teams were reporting that there was low performance of OpenMP offload. So they were seeing this on the early test and development systems that they had access to in 2020. They had increased use of mixed precision to take advantage of that, strong scaling, so forth and so on. But the first bullet was kind of important because it was really saying, hey, there's a problem here that needs to be fixed. Well, so, and make just a slight note of what all the other ones are, because the next slide is the next year's report published. And lo and behold, low OpenMP offload performance is still up there. All the others have changed. The teams have moved on, and there's various other things that they have done. Now, some of the things are positive and some are negative. So network performance is up here, not because it's so great, but because it's not so great. Maturity of performance analysis tools needs work, and so forth. So the co-development, maturation of vendor compilers is actually sort of a positive thing. So there were pros and cons. They were the main things that were important, but only one of them got repeated across both years as sort of in the top 10 items. The report has lots of items in it, but these were the top 10 that came out. And so that leads me to sort of this conclusion, which is to say, going forward, in terms of our technology risks, particularly with OpenMP and MPI, and I have sort of each on this list. So of all the items, right now, they're reporting this poor performance of OpenMP offload, both on AMD, which is what Frontier is all about, but they're also seeing it on Intel machines, on their um, test and development systems, I guess. So this 2 years of offload performance issues, what is that causing? What we saw in the 2021 report is that it's driving application teams away from OpenMP and towards other solutions, which this group doesn't want to have happen, right? So we need to try to encourage the vendors to get that offload performance up to a place where the application teams really want to take advantage of OpenMP. The other is the slingshot network performance. We need to get the MPI hardware collectives working on slingshot. So all three take us all the way to the full circle to that first diagram with the 3 yellow Exascale computers. Every single one of them uses the same interconnect, the slingshot interconnect. And so this is true no matter whether you're talking about Frontier or Aurora or El Capitan. We need to make sure that we get the vendors to enable those or get the software for those hardware collectives working in this machine. And there's, about 2 orders of magnitude improvement that you can get between doing something inside the ASIC versus in software. And then we need to resolve some performance variability of MPI calls. And I think other people have seen this as well in their codes. I know a lot of the tests that we have done on the machine, just taking all the different part of application acceptance of this big machine is to run all the MPI functions and just see how they work and run them over and over again to see if they work consistently. And what we have seen is that there is performance variability. You might call a broadcast and it goes like blazes, and 1 in 1,000 of them might run at half that speed. And it's like, but why? And it's like, it's not clear right now. There are things going on inside of Slingshot. It's a fairly complicated piece of software because it's got congestion control, it's got quality of service, it's got adaptive routing. And depending on how things are flowing around in the machine, suddenly it looks like your MPI call runs much slower than it did for the other 999 times that you ran it. So we need to resolve performance variability. We need to get the hardware collectives in these big machines working to try to take advantage. And with that, I'm going to stop and ask if folks have any questions. And thank you very much. They want to, but they are not yet. There's still some issues with the hardware.
Could you repeat the question for the people online?
Yes. Is your mic? I wanted to see if your mic was on there as we pass it on.
Hello.
Now it's on.
Can you hear me better?
Yeah. Okay. So the question was, do I know if the application teams have started to use hardware tag matching versus software tag matching on Frontier? And my answer was they have tried, but right now they're still stuck with various issues that they're seeing with hardware tag matching, and that their software tag matching is the only thing that they're using reliably right now.
Ignacio. Hello. Can you hear me?
I'll repeat the question if folks have problems.
Can you talk about the reliability of the system when they're using the full machine in terms of failures in the nodes, errors in the GPUs, things like that?
Yeah, so the way we letting people adjust it. So the question is, can I speak about the reliability of the system when they're using all of the nodes in the system?
Mhm.
And so the way we see these really big systems is there's sort of a bathtub curve in terms of early component failures. Okay, and so when you first get it delivered, there's a lot of things that are fairly marginal in it. And as you run it, and that's one of the reasons why we oftentimes run HBL right at the very beginning of its lifetime, is not so much because we want it to run fast. It's because HBL hammers the system so hard that a lot of times the weaker components will just fail and we'll replace them. And so you get to the bottom of the bathtub curve and it runs stably for a long time. And the question is, where are we in Frontier right now? Well, normally by this time, I would have expected to be close to the bottom of the bathtub curve, but we're not. We're still back a little ways in the steeper part. And why is that? Well, think about when Frontier was built. Frontier was built in 2020 and 2021, right in the middle of COVID, and that's not a problem, and right in the middle of a chip shortage, which is a problem. So there was all kinds of chip shortages and problems with manufacturing and trying to get components. We were working very hard to get all of the 60 million parts that are inside of Frontier in the middle of a chip shortage. And so what we're seeing is that bathtub curve is sloped out a little further than what we would typically see. So right now, it does have a higher failure rate than what we would expect. It's working its way down. Any other questions? Yes.
So you had identified one of the issues with MPI support on Frontier going forward as the variability that you're seeing with network performance. Is that something? So we're not on Frontier, obviously, but we've been working on Perlmutter and Crusher, which are both Slingshot 11 systems, and we've been seeing that even just at the point-to-point level, we're seeing huge fluctuations. The system will just randomly drop to half bandwidth.
Absolutely.
So
it's not a function of the size of the system. I agree.
So is that something you guys are in contact with Cray about for the Fabric?
I was
Fabric
talking with
provider?
them at 11 o'clock this morning. I talk to them every single day at 11 o'clock about exactly this, the network fabric performance, variability in particular.
Okay, and
Yeah.
do you know if they're planning to push that CXI provider upstream to the libfabric repository?
I don't quite understand the question. The CXI
So
lib fabrics, basically that patch that they put in. Well, yes.
okay,
I mean, the main thing that they did was just recompile the MPitch libraries. All they did.
yeah, I just meant we can't actually build our own copy of libfabric with CXI. We have to use the one that's installed on a Slingshot 11 system. It's not in the GitHub repository.
That's true. So, so in the case of Crusher, of course, they keep those in sync with Frontier, so you would get the right one there. But for like Aurora or for one of these other systems at the Slingshot system, I'm not sure. We would need to get the owners of that computer to ask HP for it if it's not on there.
Thanks.
Other questions?
Let me check if there's any comments online.
Joseph?
Nope.
Thanks for the talk. Maybe I missed it and you said it. Does the communication directly from the GPU into the network, is that working?
That is working.
That was working. Okay.
And in fact, that's the only way information flows, right? I mean, it has to go, the GPU, the NIC is hooked to the GPU. So if you're sending information between two nodes, it's coming out of a GPU.
Okay. Okay. So
It can come
basically-
from a CPU, but it'll end up being routed through one of the GPUs. It's bypassed through the GPU to get to the NIC, but it goes through and everyone goes through the NIC.
And is there an ETA on the hardware collectives?
No, I've been, so part of acceptance is that's all of that, that whole block of tests that we did for making sure all the hardware collectives are working. They weren't because they weren't implemented. We've moved off to be on what we would call a punch list to, for them to fix kind of once we're beyond acceptance. So we haven't gotten an ETA on that yet. We wanted to get the performance variability fixed as a more important.
That seems more important, yeah. Is there a public documentation about the limitations of this feature?
I think that the best documentation you'll have for that is to look at the Crusher early start guide or whatever it is they call it. When you go to the hackathons, they'll point it out, but it's also available right there on the website for Crusher. It's a 2 or 3 page document on the things that are working and the things that aren't working on the Crusher system, but it's also the Frontier system because they're identical software. Yeah.
Well, let me ask a little follow-up question on that. So Al, it's been a while since I looked at what they're doing on Slingshot with the hardware collectives. Do you recall what, like given the hardware implementation, there's going to be a part of the design space where they expect it to provide better performance compared to the software collectives? And is it the large message collectives or the small message collectives? I think I remember the answer, but
I don't know. Do you know, Rob? Yeah, I don't know either.
I think it's large, but compared to like the support on Mellanox, they're expecting it to be, they're moving the line down if I remember correctly, but I'm not certain.
I'm not sure either.
There's one possibility to using collective communication using multi-rail. In fact, they have some plan or something.
So I didn't quite catch the question.
Multi-rail. There are four next in the nodes. So using a multi-rail and having some collective communication. For the K computer and the FUGAC using such a 4 and 6 RDMA using collective communication at the center.
I don't know the answer to that. I know that I know that people are trying because I know I've seen some of the error messages coming by on Frontier where RDMA they're saying, oh, we're having some trouble with it. So obviously they're trying it. But I'm not familiar with whether it's working okay. So I'll have to find that out for you.
Does anybody online have any questions?
So a couple of us have hands raised. I think Abid was first.
Yes, thank you. I have a question regarding your comments on performance, OpenMP offloading performance issue. So my question is it because of the implementation support, the implementation is not optimal, or the application people are having a problem in selecting the best OpenMP target offloading to get the better performance?
I'm not sure of the answer to that question. That's why I was trying to get a hold of the document to see if from one year to the next, they both saw low OpenMP offload performance, but it could be for different reasons. It could be that they started to look at it the first year, but have run into a second reason in the 2021 report. So I don't know, like I say, I need to go either look at that document or in the case of, in your own case, you may be able to just go and look that up as well in the ECP repository or ask the teams at ECP to give you a copy of that report.
Thank you.
Yeah, I'm sorry, I don't have a more detailed answer. Maria, I think you have your hand up, or is it Stephen next?
Well, mine was actually very related to the previous question. I think I was sort of wondering your perspective on whether we're doing enough in the OpenMP, expert community to reach out to the folks, the code teams to make sure that they know how to use, these capabilities to the fullest.
Okay, that's a statement. Is there a question?
Well, what I'm asking for your perspective on that. What you've observed. I think you probably get feedback. I know you've referenced the report, but there should be more anecdotal feedback perhaps than just the reports.
Yeah. So in particular for AMD, there are monthly meetings with the ECP teams and the AMD teams that develop these software packages, and they are well aware of the features that we're seeing problems with and have been working on trying to improve both their performance profiling tools, which is a big advantage that they've had recently. Breakthrough that they had was development of a new performance profiling tool that lets you in some sense extract more or find out where the bottlenecks are in your GPU code. There's a lot of profiling tools that exist for CPUs, but they've developed one that was just made available at the last hackathon, and it's not officially released yet as a product, but they hope to soon. But similarly, it's important during these kinds of those monthly meetings to talk about some of the issues that we see, like I pointed out in my talk today. So thanks for that question, Stephen.
Yeah, thank you for the response.
Sure. Maria, did you have a question?
Yeah, I think you mentioned that the NICs can be accessed from any GPU. Somehow in your picture, it appears like each GPU is connected to a single NIC, right?
Yes, physically connected to a single NIC.
But can you access from a given GPU the 4 NICs?
Yes. So
Okay.
the software is designed so that it can route through a second GPU and out that GPU's NIC. So one GPU has a lot of information. In fact, you can imagine if you wrote your code so that it only used one GPU. Here I have a node, I have a CPU, and I'm only using one of the GPUs, but I want to get maximum bandwidth off of the node. I'd like to be able to use all 4 NICs. And so that one GPU, when it does ascend, it is possible for it to actually route out all 4 GPUs NICs.
Okay. Okay. Yeah, that was the question. Thank you.
You're welcome.
Anyone else in the room here? Questions? All right. Deepak?
Hi. So you mentioned that a number of the, most of the applications have a dependence on MPI for intranode communication. What other programming models might be used beyond MPI for that?
That one slide that I showed all the different things from SYCL on down the row are different packages that are being used by those ECP applications. Now, that's not all the possible things that might be used, but it's a pretty comprehensive list if you saw the whole ones. And so all of those are being used. But that's why I wanted to spend a little bit of time on it. It kind of shows you how much it's being used though. So what is the interest in them? It's interesting enough for somebody to use it or it wouldn't be on the chart. But in some cases they're very highly used, in other cases not as much, but fairly highly used, and some only kind of just trying.
So I think there's some codes some ECP codes that use SHMEM. I remember like, I don't know, 2 or 3 responses from that. All right. Any other questions here in the room?
Hi, I work in
ECP Exagraph project, which is part of AD. So I'm one of the guys who, work on some of the graph codes and probably filed an issue or two about low OpenMP performance. So, I'm wondering that whether you get a lot of, emails about different performance divergence between compilers, because I have faced it a lot. Like, one particular compiler giving me a particular some performance and the other compiler not quite. And sometimes there were initially, to start with on Crusher, there were errors, like weird errors, but mostly all the compilers are now error free, I can tell you. But the performance variations, they still remain to a certain extent. So is that the case with other projects as well? Because my project is a very small one, so I'm wondering.
It is. It's a very common problem. It's one of the reasons why there are multiple compilers on Crusher and on Frontier. And in fact, on Summit, the previous systems, we actually had as one of our criteria that it had to have multiple compilers, because our experience has been, in some cases, a GCC compiler actually has better performance than say the Cray compiler, or in some cases LVM is better. In some cases, it's not better in performance, but it actually has a feature that the others aren't supported in. And so there is sort of a mix and match that it's not, so Summit is 5 years old now, and this still exists there. I mean, some compilers are faster than others just because their optimizers are better in a particular case or not. And so that'll still be true in Frontier.
And which one is best depends on what code you're running.
Very much so.
Which I'll let you ask your question in a minute, Johannes, but I will throw out my favorite rant, which is there's a well-known member of the compiler community that says if you would just describe what your code is doing then and let the compiler take care of it, then you would get performance portability, which is, of course, an absurd statement. But
so talking about the multiple compilers, right? What is the reason that the LLVM compiler is not actually exposed to the application people and kind of hidden away and then not regularly built? And even if it's built, it's, you have to exactly know what to do to find it, to build it, and it's not advocated at all. Even though a lot of apps teams, including ECP apps teams, use it as their main compiler vehicle for good reasons.
I wish we had Todd here, because he would give us an earful, wouldn't he, about the ability to have containers and build it.
I mean, it's consistent. There's just no documentation really that tells you what model. No, it's built on Crusher, for example. You just have to add a path that someone else has to tell you about to your spec, to your module config, and then you can include LLVM, a recent build. But you don't know about it. Nobody knows about it. It's not just preloaded like the other compilers for reasons that are unclear to me. So I asked.
That's a good point. We'll try to take that back to the vendors and see what they can do about that.
Well, our solution at Livermore is to get HPE to throw away their damn modules and make it so things are installed in a sensible location, and then SPAC will know where to look. You can ask Deepak about it. He'll confirm that is our solution at Livermore. All right, so let me ask one final question, which is a nice open-ended question to end the talk on. What's next?
Well, so we'll go back to the first slide, right? So we've talked mainly about Frontier here. I hope that within a year, we'll be talking about, another exaflop machine, or maybe others from Europe or Japan as well. And then in the kind of year and a half time frame, El Capitan will be coming on, and we'll be learning even more about how to take advantage of these exascale computers. Right now, we only have one example. We need to have sort of multiple ones to really start to flesh out what are the real problems and issues and how we can take advantage of them.
All right, well, let's thank Al again.